So I just wanted to make sure before I start on today's lecture that that you had seen that I did post the derivation of the paraxial approximation for the spherical surface equation. So we just wrote down the equation last time, and I said I would prove it in a separate video. So this is the derivation. As I've said, like the math is useful to know, and it gives you an idea of how we derive such results in optics. There's a lot of things with understanding the geometry of the triangle and calculating the distances, and then we make an approximation that the angles are small, and that's the paraxial approximation when the angles are small. And when you do all that, you can, if you haven't seen it, I won't be using much of this today, so it's not like you missed out on too much for today's lecture, but it is there, so you know how to get to it if you just want to go through that derivation when you have some time. It's only like I think 15 minutes long, so it's not a super long derivation. Okay, so I just wanted to make sure everybody saw that, because I post the stuff and then I don't know if you're looking at it on the videos, since most of you, if you're in class, then you've already seen the lecture. But yeah, so and I think you've all seen that the lecture videos are also posted, so later you can review them. Okay, so at this point, let me stop the share. Really, I didn't have much more to say about talk about on the screen. So in the last lecture, what I showed you was the refraction spherical surface fraction. And we derived through that paraxial approximation, when the angles are small, we derived this equation. Okay. And this is also called the Gaussian approximation or paraxial approximation for the refraction at a spherical surface. Okay. And so just to quickly remind you, here's sort of the spherical surface. Here is the object, here is the image. And what we were saying is basically the angle that these rays make with respect to the axis phi, when that is small, then we can derive this equation. And which also typically then means that the height at which they meet the lens h is also small, right? Because then you won't get super large refraction angles, angle of refraction, to make it to the image point will not be very large. And so these rays are called paraxial rays. And this will be true in most of the discussion. In most of this class, mainly we always look only at the paraxial approximation or the first order approximation. This is the first order. That's because, as you'll see when you look at the video, is that any things like the cosine of the angle will be approximated basically to 1, and the sine of the angle will be approximated to 5. So that's the first order in the expansion for the cosines and sines of the angle. Okay. So this is first order, also equivalent, as I've said, to paraxial approximation, which is also equivalent to the Gaussian approximation. Okay. So having said that, since the equation does not involve any angles anymore, right? There are no angles left in the equation, which means that every ray that emits from the point S reaches the point P, which is what we want for an imaging system, that all the rays that leave the object S arrive at the point P. Okay, and of course, again, within the limitations of the paraxial approximation, what we've said is that any object point S naught will reach this point, image point SI, if they satisfy this equation. Okay, so points at the distance S naught will be image SO will be imaged to the point SI. Okay. Now, so now let's look at a couple limits of this equation. So as S naught goes to infinity, okay, which means effectively this object is receding away from the surface, the spherical surface. Okay. And when what I mean by infinity then eventually is S naught, the object just goes very, very far away from the refracting surface. So then the point P, the image point P will tend to move closer to the surface to satisfy this equation. Okay. Because on the right hand side, this is just a constant which is defined by the index of refraction and the radius of curvature R. So if S naught goes larger, okay, this term is getting smaller, so this term has to get bigger, which means SI has to decrease. Okay. And so as S naught goes to infinity, SI tends towards a distance which we call the focal point or the image focal point, okay, Fi. Okay. Okay, so again, coming back to this drawing, this vertex here, which is the point where the lens crosses the optical axis, that distance then Vp, right? So the distance Vp in the limit that S naught goes to infinity, this is called Fi, and I guess SI tends to Fi, so I've shown here, and this is called the image focal. On this side of the spherical surface, this is all some medium with refractive index Ni, and on this side is some medium with refractive index No. Similarly, we can say that the distance Vs, if now the image point P goes to infinity, right? Which means now that the rays that come out are all going to be parallel to the axis, because basically the image is at infinity. So the angles that these rays make with respect to the axis must be zero. They must be parallel rays. Okay, so that the image is formed effectively infinitely far away, which means now that the object point has to come closer and closer till this point where now the Vs at the limit of Si going to infinity, that is called Fo. Okay, and that's the object focal length. And these don't necessarily have to be equal because the Ni and No, these are not the same on either side of the medium, the glass, or whatever else you're using. Okay, from these two results, substituting for in there, so I put first S naught going to infinity, okay, and Si equal to Fi, right? So I'll get when S naught goes to infinity, that is No divided by infinity plus Ni. Now for Si, I substitute the focal length, the image focal length, that I equate to Ni minus No divided by R. From this, I can immediately write down that Fi, the image focal length, is just Ni divided by Ni minus No times R. Okay. Similarly, I can write Fo, I can solve for Fo by substituting that the image focal length is infinity, the object focal length is Fo, then I get Fo equals No divided by Ni minus N naught times R. And so from this, we get a very general relationship between the image and the object focal length. Fi divided by Fo equals Ni divided by N naught. So this is just a very general result. Whenever you have two different media with some interface, it turns out to be true for not just these spherical surfaces, but for all kinds of surfaces. So that's something that's useful as a check whenever you're doing these, whenever you calculate these things, if you end up with a relation that doesn't satisfy this. Okay. You can also see if both sides of the object and the image are the same, Ni and No are the same, then of course Fi and Fo must be equal. This will be the case, for example, when we see lenses, because usually a lens is immersed in an air medium, and then the air medium is usually going to be the same refractive index on both sides, and it ends up that you'll get that the image and the object focal lengths are equal. All right. So that is just a quick sort of consequences of the equation for the spherical surface. So now I want to talk about ray tracing, okay, because it turns out that ray tracing is another helpful way, instead of just solving equations, to understand physically what's going on in the system. Okay. And to do that, we will use that also to define certain convention, a sign convention for these rays that will help us when we do the lens equation. Okay, so the ray tracing at a spherical surface. So the first thing we'll do is we'll call a spherical surface which is of this type as convex. And what I mean by that is, so now on this side is the medium, right? The glass or whatever. And as you can see, the spherical surface is curved. That means that the center of curvature, that is the point from which all the points on the surface are equidistant with the radius of curvature r, from this point C, that point C lies to the right-hand side of the vertex V. Okay. So this is called a convex surface when C lies to the right. By right, of course, okay, we should be careful, right? Because we can always choose. I guess what I'm trying to say here is, if I had drawn this surface like this, okay, and I drew this surface right here, where the refractive index is on this side, well, that just flipped around this axis. This is still a convex surface, even though it looks like the vertex, the center of curvature, lies to the left of this surface, right? Does that make sense? It's because it basically the center of curvature lies in the medium that we are making the lens out of. Okay, so but usually in optics, our convention, and I advise all of you to do this, is to flow the rays from the object to the image point always from left to right on your paper, and not try to go the other way. You could always do that, but then you have to be careful that you're using the right convention. And the convention here then is that the radius of curvature of this object r is greater than 0. Okay. That's the sign convention for this surface. Okay, so if C is to the right of V, then R is positive or greater than 0. Now we will use an object which is exactly a focal length away, and as we just saw, that is the object focal length. Then the rays that come out from this object, right, an object point, as we just saw, all the rays that come out from this object are going to end up parallel to the axis, including, of course, the central one that's along the optical axis. So all of these come out parallel. Such an object S, from which all the rays appear to diverge from that object or emanate from that object, is called a real object. Okay, and I'll very shortly introduce what a virtual object is in a minute. Okay. And since this object was located exactly at a focal length f0 away from the surface, this also indicates that f0 must be greater than 0. Okay. This is the convention for spherical surfaces, that for a real object, f0 is greater than 0. Similarly, we can draw what happens for a real image. Same idea. Now, a real image, as we have, again, this is the medium, and again, this is a convex spherical surface. So the center of curvature is to the right of V, and the radius of curvature is greater than 0. A real image is one to which all the rays are converging. Okay? So a real object is one from which all the rays are diverging. A real image is one for which all the rays are converging to it. That's exactly what happens here. And as you know, since these rays are occurring at infinity, again, the object is very far away, so the object distance is infinity, then this distance, as we know, now becomes the image focal length, Fi. So Fi is now greater than 0. Okay. So this is a real image. So that's our convention basically. For a real image and a real object, we want the focal length f0 and Fi to be greater than 0. Okay. So how do I get a virtual object? Well, one way you can see that is if instead of allowing all these rays to converge towards this point, I interrupted this by another surface, then those rays don't appear to actually meet anywhere. Okay. All right. So let me draw that in a different way. So whenever the rays, instead of appearing to converge from our object, instead they're appearing to diverge from the object. So here's a possibility. So now I'll draw a concave spherical surface. Okay, so this is a concave spherical surface. Again, this is the medium on this side. Okay. And now imagine that those same rays that were appearing to converge towards that real image met this surface instead. Okay. Now clearly there's no object, right? Because all the rays are converging towards a point. They're not appearing to emanate from this point S. But if I drew these rays forward before they got interrupted, they appear to be meeting at this point, okay? And that point is called a virtual object. Okay. So this is the point S, and that would be, now this is the focal length, right? And the reason, of course, is still these rays are going to be parallel to the axis, just like here. Okay. So now the object focal point, or the object focal distance, Fo, is negative. And you can see that it's lying to the right of the vertex, right? So this distance is Fo, and it lies to the right of the vertex. And of course, for this concave spherical surface, the radius of curvature is also now negative because it lies to the left of the vertex. So R is lesser than 0. And Fo, the object focal distance, is also lesser than 0. Any questions? Because this point often confuses students a lot. So this is a virtual object. And the most common ways in which this shows up is in systems of lenses or when you have multiple refracting surfaces. Because then the rays that might be created by one surface, just like in this example, you had rays that were appearing to converge at this, that were going to converge at this image point. But if instead now you broke this up and you put a concave spherical surface here, now you see that there's no image that is formed directly. Okay. And this point here, where previously there would have been an image, serves as a virtual object for this surface. Okay, the second surface. So that's why we need these definitions for what we mean by real and virtual objects and real and virtual images. Okay. And so the virtual, when it's a virtual object, that distance from the vertex will be negative. Okay. So that's why you might have a negative distance, negative object distance, when that object is located like this from a place where actually the rays are not, emanating from that point, but they appear to be converging towards it. And of course, we can then also define a virtual image. Those would be where the rays, so again, go back to our definition of a real image, which is easy to understand. Here the rays appear to be converging towards the image. Obviously, for the virtual image, it will be the reverse. It will appear that the rays are diverging from that image point, from the virtual image point. Again, the concave spherical surface is an easy way to see that can happen. Because now let's take that same concave spherical surface. Okay. And now imagine that the rays are coming in from infinity. Okay. Now they're going to diverge away because of refraction at the surface. Okay. And because they're diverging away, it looks like if I extended these rays back, they would appear to me at this point over here. Okay. And so that, and because the rays started at infinity, because the object distance is now infinity, right? This distance here is the image focus, Fi, which is now lesser than 0 because it's to the left of the vertex V. Okay. And of course, I already said that there's a concave spherical surface, so its radius of curvature is lesser than 0. So this is now a virtual image. Because again, because it's a virtual image, there's nothing, if I place a screen at this point over here, I would not see anything. Okay. There would be no image that's actually formed. There's a screen which captures all the rays that are converging onto the screen. But here the rays are diverging from the screen. So this is a virtual image. How can I see a virtual image? Well, for example, you will put your eye here, right? And your eye has a lens inside, which can make all those rays that appear to be diverging from that point focus onto a point in your retina. So when you put your eye there, you will see an image. That's because it will appear like all the rays that were diverging away are converging to a point, which is over here on this side of the spherical surface. And so that will look like there is an image that is being formed. Similarly, if I wanted to make an image and record it on a film or a photographic camera, I could place a camera here with a lens on it, and then again, I could focus those rays that appear to be diverging away onto the camera, the film of the camera, the CCD chip on the camera. Okay, so that's the difference between a virtual image and a real image. There's no energy actually that's flowing into those rays until you make them happen. Okay. Of course, as soon as I put another lens here, like a camera or something, things change. This whole system looks different now, and we would have to solve the ray equations there. But that's the physical way we think about it. The intuition for the ray tracing is that it appears as if these rays are diverging away, and we can make them again, appear to be emanating from this point, which is a virtual image point. Okay. All right. Any questions about virtual objects and images? Very solid on that. Great. Okay. So to summarize our sign convention, which is very important, we will be using this a lot. So whenever the object distance and the object focal length are to the left of the vertex, they are viewed as positive. Similarly, the image focal length, the image distance and the image focal length are positive to the right of the vertex. And R, the radius of curvature, is positive if the center of curvature C is to the right. Okay. So this is important conventions that you should know when you're solving all of these spherical surface formulas. Oh, one other thing I should have mentioned before I go on. Pretty clear on the sign convention? Okay. One other thing that I should have mentioned is that if I go back to the formula for the spherical surface, we can take one other limit that I forgot to talk about. So again, the spherical surface formula is NO so plus NI by SI equals NI minus NO divided by R. Okay, so remember again, picture is there's the surface of some type, there's the object, here is the image. Okay. Now, if the radius of curvature goes to infinity, because we've been looking at object going to infinity, image going to infinity, etc. What do I mean by the radius going to infinity? What does that surface look like if the radius of curvature goes to infinity? Anyone?
Flat.
Flat, exactly. So if you have a perfectly flat surface with some medium in there, and you have the object and the image, well, according to this formula, we can solve for that. NO by SO plus NI by SI equals 0. And that gives us SI equals minus NI divided by NO times S0. Okay. Well, so this, of course, we could ask ourselves, well, is this formula right? By that I mean, if I were to solve for the apparent depth of an object inside, when viewed from inside a medium, so like if I were to look at yeah, it's good. Okay. So if I were to look at a medium, like I've just drawn over here, okay, and I ask myself, if I have an object that's on this side of the medium, right, this is S now, okay, then where does the rays coming out from this object appear to be, so like for example, if you have an object inside water, right, or inside glass, then the rays, when they come out, will diverge away because the object has a higher refractive index than the air. So this is air and water. Remember, we talked about this last time, that it appears that a spoon bends inside water, right? And the reason for that is exactly this, that now the apparent image that is being formed, and this is actually an example of a virtual image right here, right? Because you wouldn't see these rays converging towards this point, they're diverging away from this virtual image point, okay? And so if I call this distance now SI, this distance, of course, SO, okay? Well, you can now use Snell's law, okay? I won't go through the derivation. I have it here. If anyone is interested, I can show you later. But basically, you can solve for the Snell's law for the angles. You can solve for the depth SI and S0, and just by writing down from the triangles, you can calculate the angles, tan theta, etc. Okay, you do the math, you get exactly this equation over here. So we can verify from Snell's law, and of course, for small angles, because remember, our equations were all written down, the spherical surface equations are valid only in the small angle approximation, or axial approximation. So in that approximation, it'll turn out this is the exact same formula that you get for the apparent depth of an object inside, say, water or some other medium. Okay? Just a little exercise if you're thinking about it. You can solve that and show that is indeed correct. Okay, so we have considered all the limits of the spherical surface. One last thing is something called magnification. Okay, so this is an important concept. It shows up again and again. So we will just discuss this for the spherical surface as well. Again, going back to our example of what happens when you put something inside water, you may have noticed that even the size of the spoon appears a little different inside the water than it is outside. It appears like the spoon is stretched a little bit, as well as with the bending. So that is again due to of course, it's due to Snell's law ultimately, but we can also talk about it in terms of this concept, which is magnification, which I'm also sure you've encountered when you think about cameras and zoom lenses and things like that, but we'll make this a little bit more systematic. Okay, so again, we have the spherical surface, okay, and we have, let's say, the object point, and I guess I changed okay, this is object point 1, which is on the axis, and now I'm going to look at an object point 2, O2, which is off the axis. Okay, because magnification often deals with the size of the object. And so to consider the size of the object, it's not enough just to think about the position of the image. The position of the image is, wherever this is located along the axis. But we also want to understand how do things off the axis, meaning perpendicular to the axis, how do they transform upon the refracting at the spherical surface. Okay, and so now I have here, let's just still call this P1, and then I'll show you in a minute from the ray tracing that this must be P2. Okay? Well, we know that this must be the limit because we can just take a ray that goes through the center of curvature, and we know from just the angles that this must go through it can go through with some angle. Let's make that angle a little different so it doesn't. So we have the Snell's law at that interface, right? So that's the angle it bends after it meets the interface. Okay. All right. So this distance, if I call this as y0, the height of the object, and then I call this the height of the image point. Okay. So we see that. And how can I find another ray? Well, another ray might be one that is perfectly normal, that comes at normal incidence to the interface and goes through them undeviated to meet at this point over here, which is P2. So this is the image point. So P2 is the image point of O2, and so those are conjugate points, as we have discussed. The conjugate points are using Fermat's principle. And of course, such a ray that goes normal to the interface must meet at the center of curvature. So this ray goes right through the center of curvature by definition of a spherical surface. Okay, so we have this angle. Let's call that theta1, and this is the refracted angle theta2. Okay. Then we can immediately see from this triangle, this distance is S0. So tan theta1 is equal to H0, or sorry, not H0, Y0 divided by S0. Similarly, tan theta2 on the right hand side will be Yi divided by Si. And of course, in the paraxial approximation, tan theta1 is approximately equal to theta1. So this is approximately, maybe I should have written this as approximation on the left hand side. That's approximately theta1, which is equal to Y0 divided by S0. And this is approximately theta2, which is Yi divided by Si. Okay. And again, from the Snell's law at the interface, we have N1 sine theta1 is equal to N2 sine theta2. Sorry. I guess I call this NO and I. NO sine theta1 sine theta2. And again, making the same small angle approximation, we have theta1 NO is approximately equal to Ni theta2. Okay, substituting all that for solving for the magnification, which I call the transverse magnification, which is the ratio of the heights of the image, Yi divided by Yi. Okay, that makes sense. That's what I would call as magnification. That gives me minus N1 or NO divided by Ni times Si divided by Si. Okay, just substituting all that. So this is how I would calculate the magnification. If I know the object distance and the image distance, you can see if NO and Ni are equal, then it's just simply minus Si divided by So. What does the minus sign mean? Well, if YO is above the axis, okay, and so according to our sign convention, remember Si is positive when it's to the right of the surface, So is positive when it's to the left of the surface. So according to our sign convention, Si is positive in this case, So is positive in this case. Therefore, this number must be negative, right? This magnification will be negative. Whether it will be less than 1 or greater than 1, we don't know. That depends on the surface and its parameters, but it will be negative. And what that means is that an object that's initially upright over here will be inverted when it is imaged. Okay. Yeah.
The ray from O2 to C.
Yeah.
Is that supposed to be a straight line?
It is. I couldn't draw it very well.
Why is that straight? Why doesn't that?
Why doesn't it bend?
Yeah.
Because a ray that goes through the center of curvature of a surface is normal to the surface, because all radii of curvature are normal to the surface when they meet the surface for a spherical or circular interface.
Okay.
Yeah. So this angle is always 90 degrees, which means that this is at the incidence angle according to Snell's law would be zero, right? Because it's normal to the surface.
Okay.
Okay. Yeah, of course, for spherical surface, what I really mean is it's normal to the tangent to that. Good question. Thank you. All right. So again, so we make the sign convention. So yi above the axis, or yo or y, just say y, whether it's o or I, it doesn't matter. Above axis is positive, and below axis is negative. And so what this means is that if I chose an object that is upright with the arrow, pointing up like this, then yi, the distance below for the image will be below the axis. It will be always the opposite or inverted with respect to the object. Okay. So at this point, we can now talk about the thin lens. And again, the math of this is fairly straightforward, so I'm going to just put it into a video again. I'm just going to tell you the result and the way in which we approach the derivation. And then let's talk a little bit about lenses in before we go to ray tracing of lens. Okay, so the idea of a lens, of course, we discussed the idea of a lens from Fermat's principle, where we saw that the idea of a lens is if I take some, piece of glass, I have to make the optical path length here slow down, or the optical path length here longer, so that it can, it can take an object over here and image it to a point P over here, right? We saw that already. We showed that to do that these surfaces will have to be either ellipsoidal or hyperboloidal, for example, to actually satisfy this equation. Okay, the Fermat's principle, where we need this optical path length and the optical path length at the edge of the lens to be equal to each other. Okay, but now we're doing it for a spherical surface, and we've already solved the equation for the spherical surface at one interface and at the second interface. Okay, so if I take these to be spherical surfaces, this one is a convex spherical surface, and this one is a concave spherical surface. Does everybody see that? Because in this case, if I didn't have the second interface, the radius of the medium, which is the glass on the right-hand side, the center of curvature lies to the right-hand side, okay, to the right of the vertex. Whereas in this case, right, it's going to the left-hand side. So, in fact, this kind of thing where R1 is greater than 0 and R2 is lesser than 0, okay, it's called a biconvex. I know it's confusing because according to our convention, one side is convex, one side is concave, but I still call this lens as biconvex. Okay, sorry, that's just how it was, named way back when. Okay, so this is a biconvex. And of course, you can imagine the biconcave is going to have both of them sort of curved together. Yeah. All right, but okay, so how do we solve this problem? Well, okay, let's assume the lens has some thickness, D, okay? And now what you do is you set up the spherical surface refraction equation, we know that one, at this interface, and then the image of this spherical surface will become the object for the second spherical surface, just like we discussed earlier. Again, I'm not going through the math here. The math I'll put into the video. Okay. But the point is that at the end of all this, we will get an equation. So I'm just going to give you the final result, which looks something like this. Okay. And let's make some definitions. So the lens refractive index is n sub L. The medium in which it's immersed is Nm, and we are assuming the same medium on both sides, to the left and to the right of this interface. Okay. And okay, so in the in the final analysis, we have NM divided by SO1. SO1 just represents the object, the first point here, the object one. Okay. Plus, and as I said, there's an intermediate virtual object, and that now serves to give you an image at the point 2. Okay, this is the second object. We can ignore all this. In a minute, you'll see this all becomes much simplified. And as I said, when I do the video, I'll make all this much more elaborate and clear. But for our purposes, we just want the final equation and to make an approximation. Okay, so this is a fairly complex looking equation, but if you put d going to 0, which is called the thin lens equation, so d goes to 0, then this last term completely drops. Okay. Again, as I've said, how we get all this will become clear when you watch the video that I'll post. Okay. But it just follows a general idea of like taking the virtual object from one and making, or taking the image from one and making that a virtual object for the second. Okay, so with that expression, and now we just have 1 over SO1. I'll drop these indices, they don't matter, there's just an object and an image now. 1 over SO plus 1 over SI equals NL minus NM divided by N sub M times 1 over R1 minus 1 over R2. Right? And in fact, what we have done is this can be rewritten. If I call this entire term on the right hand side as 1 over F, since NL minus NM divided by NM, and typically, our lenses and so on are going to be in air, so this is going to become simplified even more. Okay, so this is just, so if NM equals 1, then the focal length 1 over F is just N sub L minus 1 times 1 over R1 minus 1 over R. And as I said, for a biconvex lens, we see that because R1 is greater than 0, R2 is lesser than 0, this sum is always going to be positive. Okay? 1 over R1 plus 1, it will become 1 over R1 magnitude plus 1 over R2 magnitude. Okay? After we put in the signs. So that sum will always be positive. So F focal length for a biconvex lens will always be positive. Assuming refractive index is greater than 1, which is true for all the materials that we usually use. Okay. All right, so that gives us the so-called Gaussian lens formula, which you've all already seen in your labs and tested. One over SO plus 1 over SI is equal to 1 over F. And this equation over here, which I wrote down for the focal length of a lens, this is a very, very important equation. This is called the lens maker's formula. And you can see how revolutionary this would have been back when they were first trying to make lenses and telescopes and so on, microscopes, etc., because it told them, given some glass surface or some glass with a certain refractive index, how do I have to grind it? What curvatures do I have to put on it, on the two surfaces, to give me different focal lengths? Okay. So that was a very critical piece of information, or formula that came out from our analysis, and that allowed then technology, to put in, to try and make the grinding wheels and so on with that curvature to give you the kind of lenses that you needed for all those different wonderful instruments, telescopes, microscopes, cameras, binoculars, all that stuff. Okay, and so, some of the problems that you will work with are just, of course, you can simply substitute. In some cases, that's all you need to do. Just substitute in the values and you get the answer. There are various combinations. I could give you the S0 and ask you to find SI, or I could not give you the focal length and ask you to calculate the focal length from this, etc. And we'll see some other combinations. Suppose I give you just the magnification. And I tell you now, and given the object distance and the magnification, can you calculate the focal length? Well, you can, because the magnification, as we'll see, I just erased it, but the magnification for a spherical surface we saw involved the refractive index and the height and the image and the object distance. And so the magnification is given to you for a lens, as you'll see, that's just equal to the SI over S naught, the image and object distance. I'll come to that in a minute. But it's just, various things that you could play with on this equation. Before I go on to talk about, that and image brightness, let me see if I have anything else. Ray tracing. Yeah, I want to talk about ray tracing and magnification now, but before I do that, any questions about this? As I said, I'll post the video that gives you the full derivation, but for a lot of purposes, that derivation, again, remember, some of the purposes of my derivation is to show you how to think about a problem. So if I give you a different problem, you can use that derivation to figure out how to approach that. In this case, it was a combination of two surfaces, a spherical surface here and a spherical surface there. How do I approach solving that problem using the spherical surface formula? That's what that derivation will illustrate. And that's what you should take away from the derivation. The actual, in the end, usually when you're working with this, you'll be working with these formulas, right? The focal length and this lens maker formula and the Gaussian lens formula. So in the last few minutes, let me just quickly talk about ray tracing and how that works. So, and I also told you about a couple of different nomenclatures. So we have a biconvex lens, which is this type, right? Where the lens is clearly in this shape, and then we could have the biconcave lens. Should be then like that. Sorry, my drawing is a little crappy, but that's a biconcave lens. Then we have some very useful lenses, turns out, for laser beams actually. The plano-convex lens, where one side is flat, okay? The other side is curved, okay? So that's a plano-convex lens. And then you also have plano-concave lens. Then you can have other lenses where both of them are curved in the same way. So you have meniscus lenses, as they're called, where instead of one being concave, one being convex, they're both curved the same way. So that's a meniscus lens. It comes into use in some situation when you're making microscope objectives and so on. Okay, I'm pretty much out of time, so I won't start ray tracing today. But I'm here for any questions that you might have about any of this stuff after the class. So we'll do ray tracing in the next class. Please watch for the video on the derivation. Sure, it will be posted in the same page with the video for the lecture.
Thank you.